Hi, everyone. I'm Nikhil Garg, and today I'm going to talk about driver search pricing. This is joint work with Hamid and Nazerzadeh. So a fundamental fact of ride-hailing marketplaces that's quite different from even a lot of other marketplaces is that demand fluctuates quite substantially, both on the order of weeks or within a or between days, but also within a day. So the bottom plot is from the Ride Often marketplace and shows the average surge factor in every 10 minutes in about like a 1 mile area over 3 days. And we see that surge, which is a function of demand and supply, is fluctuating quite substantially. And in fact, surge pricing has evolved as a response to this demand fluctuation. And at this point, surge is well understood. And sort of the point of it is to allocate rides to the riders with the highest valuation, but also to convince drivers when and where there is high demand. So this talk is going to be about how do we design the structure of surge. And to maybe motivate the rest of the talk, I'll spoil half the empirical findings. So what I'm about to show you is a plot that shows how does accepting a given trip request change a driver's earnings over the next 90 minutes. So I'll describe the data set and exactly what the measurement is at the very end. But for now, think of this as roughly the value of a trip to a driver of a given length. So what I'm going to have is on the vertical axis, I'm going to have the increase in the driver's earnings over the next 90 minutes because the driver took the trip over the counterfactual in which they did not receive that trip request. And on the horizontal axis, I'm going to have the surge factor. So how does this change as surge increases? And so a trip is should be more valuable to the driver. And so really, we should see an increasing line when I show the plot. And in reality, we see that that story is about half true. That long trips, here defined as longer than the median trip length, really do increase in value as surge increases to the order of about receiving that long trip request increases the driver's earnings by $30 or $40 over 90 minutes. On the other hand, short trips really don't. The value of a short trip remains the same even as surge increases. And this is a discrepancy, a gap that drivers really notice and use to prefer long trips. So this is a quote from an anonymous driver on the forum, for example, that says that they really dislike short trips, especially during surge. And so the point of this paper is really trying to, well, first explain what's going on, but seeing what can we do to fix this issue. And so let's describe potential fixes and also the structure of surge. The historical standard on all of these marketplaces is what's called multiplicative surge, in which whatever the base price for a trip is, however that's calculated, that just gets multiplied up during surge by a factor of 1 or 2 or whatever. In the summer of 2018, I was an intern at Uber's driver pricing team, which was switching this to what's called additive surge. So just a raw dollar amount is added to the base payout for each trip, independent of trip length. And so this paper is really trying to understand, is this a good idea? When is this a good idea? And maybe what other marketplaces should do something like this? And just, sort of the rest of the talk will be about trying to answer those questions. But at least mechanically, we can see that what additive surge is doing is reallocating money away from long trips towards short trips, even if the overall amount spent by the platform is the same. So in this work, we're going to be theoretically studying driver incentives with dynamic pricing. And I'm going to show why the old system or multiplicative surge doesn't work in a setting where demand and pricing is fluctuating over time. And then we're going to develop a new pricing scheme that does work in this setting and show that it's well approximated by additive surge in the parameter regimes that really matter for ride hailing. Now, of course, you can't do everything in a theoretical model. And so we're going to empirically validate our findings using public source data from Ride Often. Okay. So at this point, there's quite a lot of work in the cottage industry of ride-hailing papers, including those that look at driver incentives in space and time. happy to talk about these offline. Probably the high-level difference in our work is that we really care about the structure, the functional form of pricing in a way that you can share with drivers ahead of time. So instead of prices that maybe are determined by an optimization algorithm, it's a very simple functional form that you can show to drivers on a heat map, for example. Okay, so let's start with a very stylized model of a driver's day. We're going to have a single driver. They're going to be in continuous time with an infinite time horizon, and it's essentially a principal agent model. So you have a driver who's open at some amount of time, which means they're waiting for a trip request. The platform is going to come up to them. The trip requests are going to arrive at rate lambda, and they're distributed according to an arbitrary continuous function f. The platform is going to offer this trip to the driver and say, here's a trip. It'll take you about 30 minutes, and this is how much I'll pay you. In our model, the driver gets to accept or request this trip request, given this information. And in particular, we're going to say that the driver has a policy sigma, which is a subset of the support of the trip distribution S, which indicates the set of trips that they accept. In this case, 30 minutes is within the set. And so the driver says, okay, I'll take this trip. And that means they're going to be busy for 30 minutes. So during the 30 minutes, they're not going to see any other requests, and they're not going to be able to do anything else. But for that period of time, they're going to be paid according to a payment function W, which is set by the platform. At the end of that 30 minutes, they're going to be open for a trip, for another trip request. And at some point, the platform is going to come back to them and say, you know, here's another trip. Do you want to take it? If the driver rejects, then nothing happens. The driver just remains open for another trip request, and this game continues forever. And I'm going to formalize this later, but really what the driver cares about is their average earnings throughout this entire time period, as opposed, including both times that they're open and the times that they're busy on a trip. So a few things to point out that sometimes differ from practice, you know, depending on the day and the marketplace, is we do assume that the drivers know the trip length. This just makes our theoretical problem harder, in which we're going to try to design ex post incentive compatible mechanisms. And so if the driver doesn't know the trip length, the design problem actually becomes quite easier. The second thing that we assume is that I'm hearing some other, either myself or someone else. Okay, so the second thing that we assume is that what's called decoupled pricing, which is true in practice, which means that the amount the driver gets paid for a given trip might have nothing to do with the amount the rider is paying for that trip. What this allows us to do is we can change driver payouts. So we can change the driver function, payment function W without changing rider pricing and without affecting the demand distribution or their intensity. Okay, so there's a lot of things wrong with that model that I showed. The big thing wrong with it that I want to focus on in this talk is that the world isn't static, that really there's dynamics going on with demand and with pricing. And so what I'm going to try to capture that with probably the simplest possible way, in which I'm going to say that there's two world states. One I'm going to call regular world state and one that I'm going to call surge. And the world is just evolving in a Markovian fashion between those two world states. Now, everything else I had in the previous slide is the same, but is now state dependent. So we're going to have Poisson arrival rates lambda I and trip distributions that depend on the state. The driver now has a strategy per state, so they can accept maybe 10-minute length trips during surge, but reject them during regular periods. And the key, is, which is very important for practical reasons, is that the driver is paid according to the payment function that is according to the state at the start of their trip. So let's visualize what's going on here. This is probably the most important set of slides in the talk. If you understand what's going on here, then you understand the main things driving the results and the issues in practice. So at the top, we have our clock of just going between surge and not surge, independent of everything else in the system. And then we have our driver who's accepting and rejecting trips while surge is evolving. So for example, that the first trip request the driver gets is during surge. And so the driver compares that trip request to their surge payment policy, to their surge policy, and they get paid according to surge. Now, the next trip that they accept happens to be during regular periods, and so it looks at their policy during regular periods, and this goes on forever. Now, a few things to notice is that the state of the world can evolve either while the driver is open and waiting for a request, or maybe more importantly is that the state of the world can evolve even while the driver is on trip. And if the state of the world evolves while the driver is on a trip, then they're being paid according to a scale payment function. So in that first gray box, for example, the driver is being paid according to a surge payment function, even though surge is no longer occurring. And so what drivers really want to do is they want to get long trip requests near the end of surge, and so they get to lock in that payment function even as the world is changing. And this is really going to be driving sort of the results. Okay, so let's just formalize what each party cares about in this model. So what the driver cares about is their long run average earnings, which decomposes into, sort of roughly decomposes into their on-trip payment rate times their utilization rate. What I have up here, the decomposition is true for the single state model, and the dual state model just happens per state, this decomposition. And then we're going to say that the driver is earnings maximizing. So this function R, reward function R, is a set of both the platform's payment policy W and the driver's set function, the driver's set sigma, the trips they accept. And so the optimal driver policy is just a maximizer of the set function R given the payment function W. And what the platform cares about is the platform wants the driver to accept every trip. And so the platform wants a maximizer of that set function to be the policy that accepts every trip. And we're going to call this incentive compatible. The platform does have a few other constraints. So the platform does have what's called a driver participation constraint, which is just think of, on average, the platform needs to pay a certain amount of money. You can think of this as P as being the outside option for the driver. The second set of constraints is the driver needs to pay a certain amount of money per state. So you can think of this as, the surge state needs to pay out a certain amount of money. The regular state needs to pay out a certain smaller amount of money. And you can think about this as maybe you want to attract drivers to move towards surge, for example. And there's a lot of other really nice work that think about how do you actually set this surge versus not surge payment function, payment policies on average in order to induce drivers to move towards surge, for example. And so this is the technical challenge in the work, is to design a payment function W that satisfies all of these things. I'm not going to talk about this here, but you can also sort of derive the same thing as, the platform wants to optimize something like revenue or profit, and that decomposes into a problem where the platform is really trying to solve these constraints. Okay, so what are our theoretical findings? The first one is that, let's say we ignore the demand dynamics and we just work in that simple model I first introduced. Then the naive old pricing model works very well. In the static model, all the platform has to do is pay proportional to the length of the trip, and that's going to be incentive compatible. And this is true even though the driver is really optimizing for their overall earnings, even when they're not on trip. So even though the driver likes receiving long trips because it increases their utilization, really all the platform has to do is pay the same amount while they're on a trip. And this is really just sort of a direct result of our assumption on the exponential interarrival times of trips. On the other hand, with demand dynamics, this doesn't work anymore. So for example, if you pay proportional during surge, the driver is going to be motivated to reject short trips. But then we have a structural result, which is you don't actually have to think about the entire, think about every possible subset of the support of the trip distribution. An optimal driver policy is really going to be accept every trip above a certain trip length. And so this is a direct consequence of really what's going on in the visualization is the drivers really want long trips during surge with multiplicative pricing because it locks in higher payment even though surge ends. And then in the rest of the work, we construct a payment function that is incentive compatible. So I'm not going to go into the exact form, but it's a form that we do pricing that is sort of has a multiplicative component and then has an additive component and has a term that decays exponentially in the length of the trip. And so if you squint, you can see that this is a generalization of multiplicative pricing, but also a generalization of additive pricing, of additive surge, where there is just an additive component to the base length of the trip. And then in the paper, we show that in the parameter regimes that really matter, where surge is quite rare and surge is short-lasting compared to regular periods, that this function actually looks like additive surge. Instead of showing you the numerics, I'm going to jump to the empirical findings that sort of shows the same thing. Okay, so quickly to go through the empirics, we're going to use public data from the Ridesharing marketplace. And what's really key about this data compared to some of the other ride-hailing or taxi data that's online is that they have consistent driver IDs throughout the entire data set. What this allows us to do is to track a driver's earnings across trips, even during a single day. And so, like, why do this empirical analysis at all? Of course, there's many ways that the real world differs from the model I showed you. First of all, surge is, of course, location dependent. Second of all, sort of the Markovian assumptions really don't hold in practice. Okay, so what do? What we want to measure is what is the relative value of trips. What our theoretical findings showed is that multiplicative pricing really overvalues long trips during surge and undervalues short trips during surge. And so we want to compare the relative value of these two types of trips in the real data. And so the way I'm going to do that is we have our driver receives a trip of a certain length, and then we get to observe their driver earnings over the next 90 minutes. We're going to compare those earnings to a counterfactual driver who is nearby at the same time, but who doesn't accept that trip or doesn't receive that trip request. So what's the difference in these two drivers' earnings? With multiplicative surge, we see that long trips are really valuable compared to that counterfactual. So when we simulate with additive surge, there's a lot going on in how I construct the simulation. But sort of the upshot of it is that with additive surge and simulation, both long and short trips equally increase in value. And so this really shows that additive surge in practice would fix the issue of the relative value of these two trips. And so to quickly sum up, what we do is theoretically, we try to understand driver incentives and dynamic pricing, and really showing that in these marketplaces, you have to consider the dynamics at the order of a trip level. You can't just ignore these dynamics. And we theoretically develop a pricing scheme that works in this setting, and then we validate our findings with the right option data.